Okay. Key will be posted later today upstairs in the science building, science hall. We'll pick up with residence. Residence. I think we mentioned that one. We left off about right here. React this with HI, which product are we going to get? It's all based on what cation we get. Which cation are we going to get? Left, we're going to make cation on left or right? Well, in addition to having just more substituted positions, we also want to look for resonance. Okay? H plus, I minus. These electrons break away. We can leave cation here. The new H on that carbon. That cation is resonance stabilized. Okay? That's called a benzylic cation. The carbon adjacent to the benzene ring is called benzylic. Great place to make a cation. We get resonance structures of the benzylic cation on the previous page, right over here. We showed resonance structures of it. That's an empty p orbital. But how is it stabilized? Well, the adjacent p orbitals. We've got all these p orbitals next door, and they can donate by resonance, and we can show the resonance structures. And that's how we show that effect. If we made cation on the other carbon, if it attacked the other way, and we made cation there and H here. By the way, since this is the cation, which product do we get? That one, the iodine attacks. Why do we not get this cation? It's not resonance stabilized. Is there a p orbital next door? No. Can you show a resonance structure of this? The answer is also no. Try it. I mean, can you windshield wiper anything towards it? No, there's no pi bond. Okay? There's no lone pair, there's no pi bond, not resonance stabilized. So resonance stabilization can affect regiochemistry of reactions. Did we do these down here? No? Okay. Resonance stabilization of anions. I don't know why I thought we did this. What? Okay. Anions. Maybe not. How do you stabilize a minus? Here we got a lone pair and a minus. How do you stabilize that? Move electrons towards it? No, you don't move electrons towards a minus. That's when you destabilize it further. Okay? So we would never move these electrons this way. Because you're going to end up with 5 bonds or 10 electrons around that carbon. Okay? No. You got to move electrons away from this carbon. So these electrons, we can move them in here and make pi bond. But if you're going to make pi bond, these have to be moved out. So I call this sort of the in and out. Apparently if you just do it real fast a little bit. Mixed up my in and out there. Okay, what does those arrows give? This means we're moving pi bond in, and here we're moving the 2 electrons in the pi bond out onto that carbon. Okay, out onto that carbon. What do we now have? Pi bond here, and move that other pi bond out onto that carbon as a lone pair, and now that's a minus. Of course, you can draw in all the H's you want. There's 2 on the end there, okay? There we go. These are resonance structures. Resonance arrow, okay? Double-headed resonance arrow. Which resonance structure is major here? 50-50. We have a perfect blend in this example. That is, if we show the hybrid, what's the perfect blend of double bond and single? 1.5. What's the perfect blend of double bond and single? 1.5. Okay? BO equals 1.5, both. Bond order equates to bond length, and so both carbon-carbon bonds are actually the same exact length. If you look at this structure, it looks like, well, double bond and single bond. Double bond should be shorter. That's a fake structure. It's not real. You got to know that it's really resonance. The blend of these two. There's your hybrid. Charge. What's the charge on the N carbon? Minus, neutral, partial, negative, partial, negative. Which carbon has more negative? It's equal. So that's a perfect blend there. And there's your true structure over there. If you could take a picture of that compound, you would see electron density equally spread out all through there, with the bonds, the carbon-carbon interatomic distances being exactly the same. Down here, resonance structures. How do you stabilize a minus? Electrons away. Anytime you have lone pairs, or especially like an anion, you go start right there. Okay? These electrons can be moved in. Okay? When we move those in, something's got to break away from this carbon because it can't make pi bonds. You want to break the sigma bond or the pi bond?
Pi.
Pi. We're doing resonance. Only move pi electrons. What does this arrow movement give? Double bond to oxygen. There's 2 lone pairs. Electrons out onto carbon. That's now a minus. We didn't do anything with those pi bonds. We can keep going. These electrons in and these electrons out. So we made that pi bond, we moved them out here, and we didn't do anything there. Now we can keep going. These electrons in and these electrons out onto the carbon. If we kept going, these electrons can move here and move that pi bond out there. What does that give back? It gives back the original. So there we have 4 total resonance structures. 3 additional in the original. Which one's major? They're not equal here.
First,
Why do you like the first one better?
because oxygen's going to want to be negative compared to all the carbons.
Yeah. They all have the same number of bonds if you look at it, okay? Sigma framework is the same. 3 pi bonds, 3 pi bonds, 3 pi bonds, 3 pi bonds. All the same number of bonds. This one's better because oxygen likes minus better. Also better because the benzene ring is sort of a little bit more fixed, but mainly because it's minus on oxygen.
So the oxygen minus would
Well, it was the same answer. This is your major one. 2 reasons why. That's the main reason. Question, which carbons of the benzene ring take on partial minus charge, or in real life have partial minus?
Every other.
That one, and that one, as shown by your 3 resonance structures. If we drew the hybrid, those 3 carbons would have the partial minus. Let's look at neutral molecules that have a heteroatom and a lone pair. This is going to be very similar to what we just did. The difference is when you look at this, you don't see a minus. You don't see a minus charge anywhere. But still, anytime you have a lone pair and that lone pair is conjugated, is this lone pair conjugated? What do I mean by conjugated? What type of orbital is that lone pair in?
P.
It's in a p orbital. Why is it in a p orbital? Because it's conjugated with the next door p orbital. Anytime you have a lone pair that's conjugated, start your resonance by using that lone pair. Great place to start. Just like we did before, except that was an anion. Same thing here though. Just start with that lone pair. And what can we do with it? These electrons can be moved in, and these can be moved out. What does that give? A nitrogen now plus in that fake structure. Here, resonance is going to create polarization, charge. Okay? But we know all resonance structures have same net charge. This is net neutral. Well, that's got to be net neutral. Okay? We're dealing with neutral molecules here. Lone pair is a great place to start. We can keep going. Electrons can come here, and they can come out. And it's just like we did on the previous example. Then these electrons can move in, and these can move out. And then these can move in, and these can move out. Now we get you back to the original. So here's 4 resonance structures on the board. Which one's major? This one, because there's no charge. And that's how you would usually see this compound drawn if it was shown to you. What do the other 3 tell you, though? Because we know the true structure has characteristics of all of these, what type of charge does the nitrogen have in real life?
Partial positive.
It has some partial positive in real life. And that's what you got to know from understanding resonance. So how basic do you think that nitrogen is? That is, how likely is it to go react with an H+?
Not very.
If it's partial plus, it's not going to want to react with an H+. So that helps you see why it's less basic. But of course, we've already started that if a p orbital, stating that if a lone pair is in a p orbital, it's not going to be that basic. Now, like we could ask the same question as before. Which carbons in the ring take on partial minus?
Every other.
Well, you see that from your resonance structures. Here, here, and there. And so partial minus, partial minus, partial minus. And so those are the 3 carbons that are most electron rich. Which carbons are most electron rich? Well, I just indicated the ones. And seen from the resonance structure. Question below, which amino group of the two compounds above is the most electron rich? Do that on your own. And we'll look at it tomorrow. In these examples, we have an extra group added. What you want to look for here is extra resonance structures. So we can do the same thing, but remember, we just keep going. Well, with the one of those group there, you can keep going. In one of these examples. In the other one, you can't keep going. Because remember, electrons in, electrons out. Basically, you want to draw as many resonance structures as you can, and then answer the question. And sort of rationalize what you need to look for to answer that question. Down here in B, delocalization of pi bonds to heteroatoms. Okay, down here we're also going to have a neutral compound. And we got lone pairs. But these lone pairs are not to be used in resonance. Why not?
You'd lose an option.
What type of orbital is those lone pairs in? Those lone pairs are in sp2 orbitals, right? Or you could say, are those lone pairs in p orbitals? No. These lone pairs are not in p orbitals, so don't be using those in resonance. Okay? Don't do it. So, we can't do what we did up there where that nitrogen lone pair we used in resonance. So what type of resonance can we do down here? Well, there's a p orbital here, and there's a p orbital there, and that's overlapping to make a pi bond. Let's go back to taking stock. How many p orbitals in the pi system here? 2, there they are. How many electrons in the pi system? 2. 1 electron in each, overlapping to make a pi bond. Y'all remember what a bond is, right? 1 electron in each orbital overlapping. So you get a 2 electron bond. Okay. By the way, up here real quick, how many p orbitals in the pi system?
7.
7. How many electrons in that pi system?
6. 8.
8. 2, 4, 6. Lone pair makes 8. Okay. So what can we do down here with this neutral compound? You can delocalize the pi bond towards the heteroatom. Polarization. You can polarize this pi bond. All right? I'm not going to try to say too much about the theory. Let's just do it. That is, we know we got a dipole here. Okay? But the pi bond is said to be very polarizable. We can actually move these electrons up to the oxygen. And if we did that, what would we now have? Well, what does this arrow mean? There's 2 lone pairs there. What does this mean to you?
Yeah. These electrons move there.
These electrons are moving where?
To the oxygen.
Up to the oxygen to become 3rd lone pair. Yes. What's the charge of the oxygen now? Negative. What's the charge of the carbon that only has 3 bonds now?
Positive.
Positive. Of course, that's net neutral. That's got to be net neutral. This illustrates, first off, is that a resonance structure? Sure. That's the same structure, just a different positioning of pi electrons. That's what resonance is. That's a polarized resonance structure. And you get this type of thing needs to be considered when you have pi bonds to heteroatoms. Because the heteroatom pulls those electrons towards it, and you can actually show polarization. Now, which is the major resonance structure? Of course, this one, because there's no charge. But if we blended those together, what do we have between the carbon and oxygen? A single or double? It's 1.5. Well, it's not exactly 1.5 because those aren't exactly equal contributors, but it's somewhere between 1 and 2. What's the charge on the oxygen? What's charge here? See, if you could see the compound, it would look more like that than like that. It's really a blend of those. So this is more of the correct structure. It's the same old thing we said before. But typically we draw this fake structure. It's easier to draw. It obeys all the classical rules a little bit better. But it's really not true. It's really a bit fake. Okay. Show all possible resonance structures for this cation. Go ahead and do that now. This is sort of another topic. Before we move down here, what did we do above? We did some resonance of neutral molecules. One where lone pair was conjugated, one where lone pairs are not, and we just polarized the pi bond, okay? Very classical considerations for many types of molecules right there. All right, down here, resonance structures for this cation. How do you stabilize a cation? You either move electrons towards it or away. How do you do it? Towards it. Okay. There you go. Show all possible resonance structures. This question needs to be clarified in at least one way, probably two ways. Anybody want a clarification? What do you want to ask?
Whatever you want to clarify.
You tell me. You tell me. What do you want? What are you thinking? What do you want to ask about this question? Anything? I'll tell you one thing that I usually clarify with these questions, not clarify here. That involves delocalization of the cation. Why would I say that? Because look at here. I could just move these up, like we did above. There's a resonance structure. Yeah? But does that involve delocalization of the cation? No, it does nothing to the cation. So that's a little bit kind of irrelevant. It is a resonance structure, but probably what I want you to do here is show delocalization of the charge and illustrate how that's stable. Okay? So I'm really not going to count that one. Do you understand what this means? Show me some resonance structures where the charge is delocalized or moved around. Instead of localized right on that carbon, delocalized. Somebody got something?
Can you move that double bond? Like a windshield wiper?
You want to come draw it? Come draw it.
Are you gonna tell me if it's wrong before I draw it? Can I just move it here? And look like that?
Well, draw what you, instead of doing it there, draw another structure.
Wait, so
And resonance arrow. Okay.
do you like it?
Do I? Let's look at the resonance golden rules. Number 4. Look at number 4, Taylor. Resonance rules. What is the number 4 resonance rule? And tell me how you just broke it.
You tell me if it was wrong before I did it.
What was rule number 4?
Don't break octet.
Heteroatoms, especially electronegative oxygen, nitrogen, fluorine, chlorine, should always have an octet. Does that oxygen have an octet there? No. I agree, that is a resonance structure.
And I did remember the chart.
Yes. Because that is an alternative structure where all you move is pi electrons. But it's so bad we would never show it. So it's not, see, I told you this question needed to be kind of clarified. Show all possible, well not all possible good ones. Okay? Not good. No octet. Not a good resonance. Okay? Somebody got one that is good.
Not after that.
The only one that is good and that involves the localization of the cation is to use these lone pairs, move those in, and we get double bond to F, 2 lone pairs plus charge on F. That's the only possible resonance structure that involves delocalization of the cation. Now the charge is moved to the F. That is good, even though fluorine has a plus, and you might say fluorine really hates plus. Well, it does, but it's still sort of a nice guy. It does have an octet. It does have 8 electrons around it. That's doable. And if you take a picture of this molecule, there's some partial plus on the carbon and some partial plus on the fluorine. Charge is delocalized. Questions? Effective resonance on acid base. Well, I would pull out the acid base handout from week 1 because we did this. Back when we didn't know what resonance was. Which is most acidic? Well, lower pKa, more acidic. Why is it more acidic? Well, let's look at the trend here. Okay, again, we've already looked at this. This is back in the acid base handout. We really want to consider the anions, right? Get rid of the H. It's already acting as an acid. Right here. Why is that more stable than this? More acidic means it's more willing to become minus. That's it. More stable. Why? Draw resonance structures. Okay? You can move the electrons into the ring and put minus here, here, and here. Okay? Well, why is this one even more acidic? I mean, here we would have, there's three lone pairs there. Electrons in, electrons out. total resonance structures can you draw, or additional? That's one additional. How many more?
2 additional.
Electrons here, minus here, minus here. We can draw 2 more resonance structures, just like we did with the other benzene rings. How many resonance structures can you draw of that? None. There's no p orbital next door. That's an isolated anion. Is that conjugating with anything? No. There's no p orbital next door. Okay. Why is this one so much more acidic? Draw here, here. Now this ring's not aromatic. Even if it was, it would not be conjugated. How many more resonance structures can we draw? Move this where here and move what? That back out? I would just give that back, right? Why is that one more acidic? I mean, you can draw more resonance structures here.
Induction.
Somebody said it. Barbara?
The position there.
Yes. See, here the minus is spread over two oxygens. And the true structure looks like this. The charge is delocalized over 2 oxygens. Here, how many oxygens is the charge on? See, these, it puts it on carbon. Many students think because you can draw more resonance structures, it's more stable and this should be more acidic. Actually, no. This puts minus on carbon. Here, 2 oxygens more acidic, even though less resonance structure, less delocalization. Does that make sense? 2 oxygens is better than an oxygen 3 carbons. That's why we call that a carboxylic acid, and we don't call that an acid. Okay, but we can start putting groups on the ring, and we can say which is most acidic. To answer these, you want to start with the anion, as always, and then say which is more delocalized. The more delocalized the anion, the more stable and thus the more acidic. You need to draw resonance structures. NO2, we haven't seen that before. It's functional group C in organic 2. It's nitrogen with double bond to O, single bond to O. This O is minus and the oxygen is plus. So it always has 2 charges, but that's your nitro group. See nitro compounds and like rohypnol. So answer that question there. Effects on basicity. Which of these 3 is the stronger base? Higher pKa for the conjugate acid means it's a weaker conjugate acid, stronger base. Why is this base stronger than that one? Well, we're talking about the nitrogen. When we're talking about a base, we're talking about the lone pair reacting with the H. Well, the question really is, which lone pair is more reactive? The one that's isolated on nitrogen and no conjugation, or the one that's conjugated with the pi system? Okay. That lone pair is conjugated. It's busy doing p orbital stuff. We drew resonance structures top of the last page. This lone pair is isolated. And actually, in terms of charge, remember that nitrogen has a partial plus? I mean, why would a partial plus want to attack an H plus? It doesn't want to do it as much as this one. It's less acidic. I mean, it's less basic. Now we get over here, this guy's actually non-basic. Now these two may look pretty similar. This is almost non-basic. What type of orbital is that lone pair in? You see, it's also conjugated. If we do resonance, we get resonance structure. They're both conjugated, and at some point I told you, a lone pair that's conjugated is not going to be basic. Okay? But why is the difference here? Well, the difference here is a little more subtle. In which compound are the electrons pulled more into the pi system? That one there, because the oxygen is pulling them more towards it, into the pi system. And that really decreases the basicity. Here, the carbons don't pull the lone pair quite as much, and so it maintains a little bit of basicity, but it's not as basic as this one, where the electrons are just sitting right there on the nitrogen. Questions like this: which nitrogen has the highest electron density? No. Here it's delocalized, as shown by the resonance structure. And we could ask questions down here. Again, these are all opportunities to draw resonance structures not only into the ring, but also potentially into the other group. And one of these you can draw a resonance structure into the group, and one you cannot. Then answer the question: which nitrogen is most basic? Resonance of radicals. Let's skip that for today. We might look at that when we look at these tomorrow. Draw some resonance structures, answer those questions. Golden rules of resonance, and then on the back is that Charlie Brown and some other guy. Okay. Chemistry of dyes. I know you've been dying to get to this chemistry. Some questions there. Questions there. Diels-Alder. Other questions? Types of things we hope to be able to answer as we move through this material. We've already done A, conjugated, non-conjugated, accumulated. That was on the previous handout. We'll start with B. Nomenclature of dyes. Very similar to other. Longest continuous chain. 1, 2, 3, 4, 5, 6, 7. If you heptane, we got more than just one alkene. If it was one, it'd be a heptene. Since there are two, we don't call it heptene, we call it heptadiene. So the little modifier, di, tri, etc., goes right before the ene part. So dienes are called heptadienes, octadienes, butadienes. Okay? But we need to say where the double bonds are at, because, I mean, I could give you a 1, 2, 3, 4, 5, 6, 7. I mean, that's a heptadiene. Where are the double bonds? Well, lowest numbers. That's going to be 1, 2, 3, 4. This would be a 2, 4 heptadiene. Basically, with the two numbers indicating where the double bond is at. What would this be? 1, 6 heptadiene. Constitutional isomers. With this one, we have something else to add because, for example, what is this over here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. What is this here?
2, 4 heptadiene.
They're both 2, 4 heptadiene. What's the difference? They're stereoisomers. What do you want to put in front of this one? Each double bond can be cis or trans. Here, this is trans-trans. This is trans-cis. So instead of using cis or trans, let's use E or Z. That's what you would use here. Each double bond here is what? E. Sometimes you can say E, comma E in front. That's not ambiguous because obviously each one is E. It might be better to say 2E, comma 4E heptadiene. But basically up here, your first letter goes with the lower number. Let's do one over here. What's the difference? What's this going to be called? That one's E, but this double bond is the same size with Z. So this would be Z, comma E, and then the same name. Z, comma E, 2, 4 heptadiene. Don't forget your EZ when possible. Back over here. Do you need EZ over here? You don't need it over here. That double bond is not stereogenic. Neither one is. So you don't need any stereochemical descriptor over here. Let's name this one. Longest continuous chain. Both alkenes have to be in the longest continuous chain. So you might as well start right here. 1, 2, 3, 4, 5, 6. That's the only way for both to be there. So what we got here? Hexadiene. Where are the double bonds at? Well, it's 1. If that's 1, 1 and 5. If that's 1, this is 5. Either way you go, it's 1, 5. Which one do you want to be 1?
Chlorine.
Chlorine, yes. So it's 1,5-hexadiene. What's on the 1,5-hexadiene? We have a chlorine and a propyl. Chlorine's at the 1, propyl's at the 2. So we got 1 chloro, 2 propyl, 1,5-hexadiene. What do we need to put in front? E. So that's E. There's no E or C there. Obviously the E goes with the things that it goes with. Okay, please look below. There's something about terpenes. Please do some reading about conjugate addition. 1,2, 1,4 additions. And we can try to work some of these problems over here. And then in the back, you'll find Diels-Alder. Please be reading about Diels-Alder reaction, common reaction of dienes. And that'll be that handout there. I'm thinking about having a 5-point extra credit on Friday for attending a something at 11 o'clock. There'll be an information session this Friday.